The cloud is going into space. And this is not a joke. This is not science fiction. Let's get something straight. Orbital data centers are not a thought experiment. Prototypes have already launched. FFC filings are in. Solar-powered AI constellations are being formally proposed. Startups have put AI-class hardware into orbit. Major aerospace firms have completed feasibility studies. Serious people are allocating serious money. The orbital cloud is no longer a metaphor, it is a business plan. And that should probably make you sit up slightly straighter. The pitch: infinite solar, no earthly limits. Here is the sales deck. In the right orbit, you get near constant solar power, no night cycle in sun synchronous trajectories, no clouds, no atmospheric loss. Cooling: you radiate heat into space, no water shortages, no giant evaporative towers, no villages complaining about the hum of transformer stations. Land use: zero. No NIMBY politics, no grid bottlenecks, no zoning issues. AI demand exploding? Fine. Move the racks off planning. It sounds elegant. It sounds inevitable. It sounds like the kind of sentence that ends civilization chapters in history books. Radiation. The sky is not gentle. On Earth, cosmic rays occasionally flip bits in servers. It happens. Error correction handles it. In orbit, you are above most of Earth's atmospheric shielding. Charged particles, solar storms, cosmic radiation. You are running delicate silicon inside an environment that actively degrades it. Bit flips increase. Permanent damage accumulates. Hardware ages faster. That means radiation hardening, shielding, redundancy stacked on redundancy, error correction overhead becoming part of your energy budget. And here's the quiet part. More error correction means more computation. More computation means more heat. More heat means bigger radiators. Physics does not offer early adopter discounts. Cooling: space is cold. Vacuum is not helpful. People say, but space is cold. Yes, it's cold in the same way Antarctica is cold, but there is no air. You cannot blow a fan across a GPU. You cannot rely on convection. Heat must leave through radiation alone. That means large radiators. Large radiators mean mass. Mass means launch cost. Industry executives have already admitted cooling remains one of the biggest unsolved engineering problems. Overheating in orbit is not a punchline, it is a constraint. Debris: scale the numbers high enough. Low Earth orbit already contains tens of thousands of trackable objects. Add mega constellations, add millions of additional units, add AI clusters with dense mass and high value. One collision does not erase an entire distributed system, but scale the object count high enough and the probability curve stops being polite. Kessler syndrome is not science fiction. It is a cascading statistical risk. If you industrialise orbit aggressively, you increase the background fragility of the entire environment. Your cloud does not instantly become a cloud, but the sky becomes less forgiving. Geopolitics: server downtime, now with missiles. Orbital infrastructure is strategic infrastructure. Anti-satellite weapons exist. They have been tested. If orbital AI clusters become critical economic or military assets, they become targets. In a terrestrial data center, downtime is an outage. In orbit, downtime can become an act of war. Now, imagine global AI systems, finance systems, defense systems, partially dependent on assets that can be physically destroyed. We have taken a cloud and made it kinetic. This is present tense. Some advocates argue this is the inevitable future. They say falling launch costs change the equation. They say constant solar makes it the lowest cost compute in the long run. Others, including leaders in AI itself, have called large-scale orbital data centers economically absurd for now. Launch costs, radiation exposure, refresh cycles, failure rates. When the people building the AI arms race cannot agree on whether the sky is a server rack, that is interesting, because it means this is not hype. It is a live argument. Maintenance, please submit a launch request. On Earth, if a rack fails, someone replaces it. In orbit, failure means robotics, expensive servicing missions, or writing hardware off entirely. Radiation shortens life cycles. Debris risk shortens life cycles. Upgrading means launching new mass. Hardware refresh is no longer a procurement cycle. It is a mission plan. The green question. Yes, solar in orbit is abundant. No, rockets are not carbon neutral. Manufacturing radiation-hardened electronics is energy intensive. Launch emissions are real. Rebuilding after failures is not free. Whether orbital compute is greener depends on full life cycle accounting, not just the elegance of sunlight above the atmosphere. The glow is clean, the supply chain is not. The psychological reveal. Here is the part that fascinates me most. AI demand explodes. Energy constraints tighten. Water becomes scarce in some regions. The instinct is not to slow demand. It is to expand the envelope. Too hot? Go to space. Too constrained? Go to space. Too competitive? Go to space faster than your rival. Nobody slows down because nobody can afford to slow down. It is the same treadmill dynamic driving AI scale right now. Moloch has discovered orbital mechanics. Final thoughts. Industrializing the sky. Putting data centers in space is not absurd. It is technically conceivable. It is partially underway. It might even work at some scale. But it concentrates risks into an orbital shared layer exposed to radiation, debris, geopolitics, and physics that does not negotiate. We are very clever. We are very competitive. We are slightly incapable of restraint. And when a civilization decides that the solution to planetary limits is to industrialize the sky, it is worth pausing. Because if the cloud goes down this time, nobody tripped over a cable. We will have reached up, built something fragile above our heads, and called it progress. What could possibly go wrong?